Alright, this is the Tutor Wizard. Please subscribe right here. You'll get notifications for this series, this video, other videos in this series. I don't know what this series is even. It's going to be in the special interest, but I really wanted to do this today, so I'm going to force feed it down your throat. What are we going to do? We're going to do the analytic power series representation of the period of a simple pendulum. Basically what we're going to do is I'm not going to derive any of this. I'm just showing you with a scenario what's going on here. We'll let the physicists do this. I'll take it from there. Once we derive what we think the equations are, and the differential equation, the second order differential equation we get to, which describes this, and classically they say when theta is small, then we can approximate this with sine theta is approximately equal to theta, so then we can put a theta in there and then get the linear approximation to this guy, and they can do this kind of thing. Otherwise, whichever technique they use, and Huygens is one of the first ones to do it, and it becomes Huygens' law. This is the first approximation, or the good approximation to what the period of the simple pendulum is. That's why they call it T naught. If we want to call it T and put a T there, we would have to, what would we have to change? I'm going to erase it right away, but if that was T, oh no. T, the real period is approximately equal to that, where, sorry, L is the length of the rod, and G is the force of gravity. Actually, they're using this and to define a meter. The first time is how he does this. He defines a meter and figures out what the force of gravity is, and he finds out that near the equator it's approximately equal to 9.8. 0 near the equator, 1 they notice in some of the papers is approximately equal to pi squared. That's because it comes out of this derivation, you'll see. What we're going to do is we're going to solve this. This is elliptic integral of kind 1. What? Yeah. These hot messes, these are extremely hard to solve. We're going to do it right now. From the simple pendulum, if you have a pendulum of length L and it's swinging back and forth through angle theta naught, what we want is the period is going to be the amount of time it takes to go through one full revolution and return to itself. So that's what's going to happen. That's the T that we're looking for. The amount of time it takes for the bob, the blue bob, to be swinging and do. If I fix and I started here, I want to know from this, and then it goes and then comes back. I want to see the period T of how long that takes. And from that you can define meter and then get the gravitational force of Earth from these types of calculations. Is why they want these. This is the first term, essentially the first approximation. Explicitly, what do we get? This is all we needed to start with. Bye-bye! That was just to show you. This. Oh, I needed the T naught. Who was the T naught? This guy. What I'm going to do with this now is I'm going to put that into where T naught is. Then I'm going to change drastically what that looks like, and then we're going to compute this integral by term integration of a power series representation of what this function is. Let's do that. T is equal to 2 over pi times T naught, which is 2 pi root L over G times this junk. Who's this junk? The integral from 0 to pi over 2 of, let's go slow. 1 over the square root of 1 minus k squared sine squared x dx. From here, I like this a lot. The pi's will cancel. T equals 4 root L over G. I was going to put it in cleverly, but let's keep it out. Now what do I have? This guy, the integral from pi over 2. This, first of all, it doesn't matter what calculator is doing. I'm going to do something extremely clever with the machinery of this because I want to show, but regardless of where we're doing this, I don't like the square root, and that doesn't really help me. And if I have to take a derivative, or I'm doing something with a function and it's got square root, that doesn't really help me. I want to turn it into this is a negative 1/2 exponent is what that is. So I'm going to write this like this: 1 minus k sine x squared. I can combine those guys. What I just did was a squared b squared is ab squared. There's an exponent law in reverse. Oh, look, they're everywhere. Doesn't matter what you have, the rules never change. Now the square root 1 over is negative 1/2. And again, Sir Isaac Newton, coincidentally, self-isolation. He had to go from London from the bubonic plague in the 1666, roughly, 1665, 66, somewhere in there. They're doing this. And there's a bubonic plague in London, so he's hiding in the farm, and he systematically develops or single-handedly develops the notion of the spectrum of light, the first rigorous theory of gravitation, and the calculus of variation, all in 16 months, hiding in self-isolation. What have you been doing so far in self-isolation? Yeah, that's right. Maybe you should get off your ass and do something like develop the theory of gravity or something. Nah. Or just eat some chips. I'm going to do this. What was I talking about, and why is he coming up? Because now I'm going to use Sir Isaac Newton's binomial theorem to show how to do what this function to this negative exponent is. He tells you 1 plus x to the k for any k can be written as the sum from n equals 0 to infinity of k choose n x to the n, is what Newton says. Thank you. He said a lot of stuff. He thought he also was going to make gold somehow in alchemy. Can't get everything right. Using this on this guy, and I have a minus, remember. This is equal to 4 root L over G times the integral from 0 to pi over 2. What do I get? This is, the sum from n equals 0 to infinity of negative 1 to the n, k to the 2n, sine to the 2n x, times negative 1/2, choose n. Normally they put that in there, but I forgot it as I was talking. dx, don't forget that. I'm not doing Lebesgue integration. No, Riemann dx. Now we're going to swap them. This is term-by-term integration. I can switch these two. This is a constant, this is a constant, this is a constant. Equals. Switch. Okay, this sum, you're like, they all look the same to me. Close. Sum and sum, they are both sum symbols. One's an infinite, one's a, oh no, they're both infinite. What's going on? Sum from n equals 0 to infinity of the integral from, no, these guys are all junk, I said, leave them out. Listen to your brain when it talks. Okay, I will. N, k to the 2n, negative 1/2, choose n, don't forget him, I know, I got it. 0 to the pi over 2, sine 2n x dx. So you can see now. And what do I have left to do? Now I have just two things. I need to compute what that guy is, and I need to compute what pentagram is. Asterisk. Let's do those two things. Choose your point. Well, we have to do both. We're going to do this one first. They're almost the same calculation in a weird way. Now what I'm going to do is just compute this guy. So erase everything else in your mind. Forget this hot mess. Task 1, I need to compute this. Leave everything else alone in your problem temporarily. Then we'll compute this, leave everything else alone, and then we'll put it back together. I need these two things. This one, where Sir Isaac Newton says this is equal to negative 1/2 minus 0, negative 1/2 minus 1, negative 1/2 minus 2, dot, 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 negative 1/2 minus n minus 1. I know. How did he come up with that? Now I'm going to have to clean this up. Remember, there's n terms here because I've started at 0. That's why I wrote it for myself. And then I've n minus 1. There's a mathematician. This is a true anecdote. I wasn't there, but apparently this is a true story. There's a mathematician, and he's going senile, and he's with his wife at the airport, and they've got 10 bags, and she's like, okay, pat on the head because you're senile. I'm going to go check us in. You just hold down these bags. Just stay here, all right? Mathematicians, they all go senile at the end, I'm pretty sure. I don't know when the tipping point is. Could be any time now. Could have happened, I'm not sure. He's waiting with the bags. She goes to check them in. She does that. Her job, success. She does that, I guess, apparently. I'll just sit here and... She comes back and he's all disconcerted and he's all upset. She says, well, what's wrong? And he says, no matter how we've lost a bag. There's only 9 bags. And she's like, no. He's like, yeah, watch. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 bags. Careful when you index with 0. There's n things here. There's n things, not n minus 1. This is equal to -1 to the 10 bags times -1/2 times -3/2. I'm adding these fractions. How am I doing it? Dirty trick. 2 over 2. 2 over 2. And then I'm adding -5/2. ... Oh, this one I will show you because careful. This is -1/2 minus. I'm going to multiply by the dirty trick. 2 over 2 times n minus 1. Don't do that in your head. Where did that bracket come from? It was that one. It doesn't matter. This is equal to, now I have a common denominator, over 2. Then I have -1 minus 2n plus 2, which is equal to -2n plus 1 over 2, which is, pull the negative out, -2n minus 1 over 2. So now I've taken the negative out. This is 2n minus 1 over 2 over n factorial. Good. How many 2's are there? Again, n of them. This is equal to -1 to the n. 1 times 3 times 5 times ... 2n minus 1 over 2 to the n times n factorial. Physicists and the book stop here. Not this wizard. This wizard's going to do this. Wizard moves. 2 times 4 times 2n. You're like, you can't do that. I know I can. I'm going to do wizard. I'm going to multiply by 1. There. What did that do? First of all, that gave me, I was missing all the even numbers. Well, here, I want them. I put all the even numbers on the top, and I do it on the bottom too. Now what I see is on the bottom, this becomes 2n factorial. Immediately, that's why I did it. But on the bottom, something really clever happens too. It becomes this again. Each one, this is 2 times 1. This is 2 times 2. This is 2 times n. Take a 2 out of each of those. You'll get 2 to the n. And what's left? 1 times 2 times 3 times n factorials left. So this gives me, why is no one else excited? 2n n factorial over 2n n factorial, 2 of them squared. And that's going to double in the, wait a second, you haven't seen, that's going to double again. That'll be squared. What? What's that? That's this hot mess. -1/2 choose n is this. The book leaves it like this guy, but I say boo on you, book. What did that tell us? T is equal to 4, the square root of L over G. The sum from n equals 0 to infinity of -1 to the n, now times -1 to the n, 2n factorial over 2 to the n factorial squared times k to the 2n, don't forget that guy, times sine to the 2n, no, integral from 0 to pi over 2 sine 2n x dx. I know it's in there somewhere, it's in there somewhere. It's in my mind palace. Sherlock Holmes ain't got nothing on me. King Kong ain't got get on me. Sherlock Holmes ain't got no deductive reasoning on me. Now what? I did the first half, that was the -1/2 business. Coincidentally also, those are going to go away. What? Exponent laws. What else am I going to use? This is product in the basis is sum in the exponent. I'll go really slow. There you go. Equals -1 to the 2n. Oh, another exponent law. Associate, that's -1 squared to the n, which is 1 to the n, which is 1. It's gone. Gone. I might drop that one. Oh, I gotta stop doing that with it. But that deserved a mic drop. Again, what do? I ignore that. I'm hoping you agree that hot man. Oh my goodness, what is happening? Ignore that. This guy. You're not going to like this either. I like it a lot. This is sine 2n x dx. And then yes, immediately Wizard Apprentice asked, so I will point this out right away. First of all, what I'm going to do is I want a formula for this. I want to use a reduction of order formula. I sniff and sense what's happening here. And I'm also going to, so I'm going to drop these to find the formula. I don't want the bounds there. I just want to crack the antiderivative egg. And I want to do the definite integral. We'll do that at the end once I've cracked the antiderivative egg and I found what the general antiderivative of this is. Then we'll put that in there. And I can just use a substitution, and then I can put a plus h where x was when we do derivatives and these types of things. Substitution, I can put 2n where n is once I have the formula for this. So now what we're going to do for this guy, to crack this, I'm going to suppress the bounds so I can remember what the reduction of order formula for this is, and instead of doing 2n with that formula and having a complicated number, I'm just going to use n and find the reduction formula for n. Then I'll put 2n back in, then I'll put the bounds back in, then we'll compute that nightmare of an integral. Remember, this is an elliptic integral of the first kind, which are impossible to, these are non-elementary functions. You can't do it without the power series. And then I see physicists try, and you're not going to get a nice tight thing like we did. Let's do it. How do I compute this? Again, you can't see because I just do the finished polished version of this, but I tried to do this earlier and I used the wrong technique first. It was like all scrap, so you'd calculate and you're like, and then you start over again. It's like, okay, let's get this right. I'm going to use exponent laws, and then I see that I'm going to turn this into something that I want by adding exactly what I need, by adding 0 again, which really makes me happy. This is, I'm going to try and use integration by parts to use a reduction so that I can reduce the n to an n-1, and if I can do that, I keep iterating it, and then I'll find a formula for how to compute all of these all the way down to sine squared, and then I know how to compute sine squared because I have a trigonometric identity, and then that's all you need to know. We're done. How do I do this? My favorite trick. Sine n minus n plus 1 x dx. I've added 0 in the exponent. Then I use an exponent law to steal this 1 off. This will give me the integral of sine. We're going to call this in, by the way. This is integration by parts where we have to solve for the appropriate integral. Fast forward to the end where I get the clever formula. And whoa, with this one, and then we'll clean it up. Sine n minus 1 x times sine x dx. So I just did this move and I took 1. That's how it's going to reduce it, actually by 2. Now what I want to do with that is, I know how to, and then you're like, well, I'm trying to use integration by parts and I didn't see that clever move. Okay, I did the clever move. You can steal it from me. But now you're like, who should u be and who should dv be all the time? Use the one you can integrate or differentiate the crap out of. I could differentiate this, hopefully. You've got some rules and chain rule inside, outside, but I can differentiate the crap out of this. So u, something I can differentiate. I know how to integrate and differentiate this, but more importantly, I can integrate this, so dv. That's what it would be. So that's why I make the guess this. Use something I can differentiate. dv something I can integrate. That's why I make the choices. Integral of secant cubed x dx, tangent, pun intended. I don't know. And then a clever trick, I'm going to write that as secant 1 times secant squared x dx. Once I break that 3 into 1 and 2, and I use a couple exponent laws again, this is the reduction order formula for secant. Then what do I see? I know how to integrate this. What's the derivative of 10? That's right, secant squared. So this would be my dv. I can, what's the derivative of this guy? Secant 10. Yeah, that's how you make your guesses. This is the reduction order formula for secant. We don't want that one. We want sine. U is sine n minus 1 x. Du is by the chain rule. N minus 1 sine n minus 2 x times cos x dx. And dv is sine x dx, which means that v is negative cos x. That gives me in is equal to u times v negative cos x sine n minus 1 x plus n minus 1, the integral of sine n minus 2. Oh, that's where he's trying to go into the argument. Exponent n minus 2 times, I get a cos and a cos. I've done this before, cos squared dx. And we get to use both identities. We get to use the Pythagorean identity and the double angle identity in its reverse direction. We'll see. Now that I've done that, so I just use integration by parts to write this as integral of u times u dv is u times v minus the integral of v du. What does that do for me? First of all, we're going to get we're going to get weak derivatives. This is going to go away when we go from 0 to pi over 2. And then we can clean up this guy. What I need to do with this is I'm going to turn cos back into sines, and then I'm going to find in here somewhere again, the original integral. This is equal to, we got to write it all out, negative cos x sine n minus 1 x plus n minus 1 times cos is cos squared plus sine squared x equals 1. So cos squared x equals 1 minus sine squared x. This is the first one we want to use. The integral of sine n minus 2x times 1 minus sine squared x dx. We're going to distribute this in now. The first one will give us the reduced one, and then minus the 2 and the 2 will cancel, and we're going to get sine n again, which is our integral. This is equal to in equals negative cos x sine n minus 1x plus n minus 1 times the integral of the first one, sine n minus 2x dx, minus n minus 1 times the integral of sine nx dx. And that's what I'm saying. This is I. Not the identity matrix, the integral, the nth integral. Coincidentally, we would have to prove this by mathematical induction, but we'll spare you that too. Wait till you see the induction videos. I can't wait. Fibonacci, Fibonacci, there's 50. Prove this about Fibonacci. Prove that about Fibonacci. Prove these things about Fibonacci. I like Fibonacci. Solve for in. This will give me in plus n minus 1 in's equals this hot mess. Negative cos x sine n minus 1x plus n minus 1, the integral of sine n minus 2x dx. This one and this one cancel. Let me move it up one more time, and I get in, which is the integral of sine nx dx. Cleaning it up and dividing by n is negative 1 over n cos x sine n minus 1x plus n minus 1 over n times the integral of sine n minus 2x dx. This is reduction of order formula. What did it do? It reduces the calculation of n to n minus 2. And when you put bounds, this is going to go away and make it really slick for us. Using this now, I'm going to cheat and put 2n in there. So I2n is equal to the integral of sine 2nx dx, which is just put 2n wherever n was. This is going to be negative 1 over 2n cos x sine 2n minus 1x plus 2n minus 1 over 2n times the integral of sine 2n minus 2x dx. Now I have the reduction formula for that guy. Now we put the bounds on there and see the magic that happens. We get something awfully similar to this with a pi over 2. Putting the bounds on there and using the formula now. The integral from 0 to pi over 2 is integration by parts with the bounds says I do this, integral from 0 to pi over 2, integral from 0 to pi over 2. Now I put the bounds back on. Coincidentally, hopefully if you're watching integration and you take anything from this, this is how you do something horrible when you have to use integration by parts or a horrible, worse substitution in there. Ignore the bounds, crack the antiderivative, find what the formula is, put the bounds back on. There now, they're on there. What did that do for me? How can you see this without, if you tried to do that with all the machinery on there and all the bounds, do you see every time you compute these you would have been lost? Yeah, look, cos of pi over 2 is 0, and sine of any power 2n, I don't care what it is, sine of 0 is 0. This is completely gone out of the formula now. Good. So this is using the reduction of order formula. This guy is now equal to 2n minus 1 over 2n times the integral from 0 to pi over 2 times sine 2n minus 1x dx. We're getting a recursion relation from this. This is extremely strange, this recursion relation. We're going all the way down to a0, and I need to know what a is. Actually, we'll go to a2, and then we'll compute a2, because a2 will be the integral from 0 to pi over 2 of sine squared. This is a recursion relation with the integral inside of it. I2n's. What is this formula? Let's keep going with that now. I'm going to reduce this one, iterate, prove by induction that it always works. We did. This is how you get the pendulum. This integral is equal to 2n minus 1 over 2n times the integral from 0 to pi over 2 sine 2n minus 2x dx. Run the integration by parts formula again. The cosine term goes away. Run it on this. Now I have this number. You're going to subtract 2 and get this same formula. This is 2n minus 1 over 2n. Running the recursion relation formula on this gives me 2n minus 3 over 2n minus 2 times the integral from 0 to pi over 2 of sine of 2n minus 4x dx, which equals dot dot dot, keep doing this all the way to the end. I get equals 2n minus 1 over 2n, 2n minus 3 over 2n minus 2 dot 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 3 over 4 times the integral from 0 to pi over 2 times sine squared x dx. Remember, in the last steps before I do this, this would be when for sine 4x, n is now 4. The reduction formula says I do 3 over 4, the integral of 4 minus 2, which will be 2, and then this will be the last one where we're going to compute this one using another trigonometric identity. What does that give me? This gives me equals 2n minus 1 over 2n times dot 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 times 3 over 4 times the integral from 0 to pi over 2 times 1/2 1 minus cos 2x dx. I use the trig identity. Our last piece, the integral from 0 to pi over 2 of sine 2n x dx is equal to this now, and now it leaves us to have to calculate this computation. This gives me 2n minus 1 over 2n dot 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 times 3 over 4 times 1 over 2 times, this is x minus 1/2 sine 2x evaluated from 0 to pi over 2 by the fundamental theorem of calculus part 2. This guy's 0 both times. Why? At pi over 2 it will be sine of 2 times 2 sine of pi, which will go away, and at sine of 0 will go away. And then at 0 I get this is gone. So the only one term that stays in these 4 terms, fundamental theorem of calculus, f of b minus f of a, this one stays pi over 2. The integral from 0 to pi over 2 sine 2n x dx clearly equals 2n minus 1 over 2n dot 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 3 over 4 times 1/2 times pi over 2. We're not done. Oh, look, it's the odd numbers multiplied. Yeah, okay, so let's do that again. What does that become? Notice in the same dirty trick that I'm about to use, this is the product of all the even numbers. So I can factor a 2 out of this, I can factor a 2 out of the 4, I can factor a 2 out of the 1, and this will give me 2 to the n times n factorial. I'm going to do it again. I'm going to multiply by 2n times 4 times 2, all the even numbers, over 2n times all the even numbers. So I multiply by 1, it doesn't change anything. And now I get on the top, this is 2n factorial on the top times pi over 2 to the n factorial. There's one of them, and then I get 2 to the n factorial again. So squared, almost identical. And then don't forget, that's why I keep him out. There was an extra 2. So that's what this is. The integral from 0 to pi over 2 sine 2n x dx is clearly equal to 2n factorial over 2 to the n factorial squared times pi over 2. Well, how do we get pi? What's the Arctan power series representation? You can get pi. Pi is 4 times the power Arctan of 1. What does that give us? That junk is this. We can put that in there now. This guy's gone. We can actually do that from here. We get to put that in there now. This is 2n factorial over 2 to the 2n, no, 2 to the n factorial squared times pi over 2. Here we go. Now that we have that, we have an explicit power series representation for the periods of the simple pendulum. In particular, if we take the first term, we get Huygens law. Huygens ain't got crap on me. Okay, maybe he does that. Don't stop comparing yourself to Huygens and Newton on the internet. I'll do what I want. The sum from n equals 0 to infinity. Gone. Look, this one and this one, there's 2 of them. So 2n factorial over, okay, let's leave that. 2 to the n factorial squared. That is squared now. Squared of the squared of the squared. That's quartic. What'd you call me? 2 to the n pi over 2. Remember who's k? He's a sine function. Equals 4 the square root of L over G. The sum from n equals 0 to infinity. 2n factorial over 2 to the n factorial squared times pi over 2 times, that is the period of a simple pendulum, Huygens. That. If we take the first term where n equals 0, let's see, does that happen? I claim it is, and you're like, I don't know, but yeah. Let's see if it collapses to this by taking the first term. Plus, what does any of that mumbo jumbo mean? This is a sum. I'm adding, there's a bunch of terms, you just add ... Instead of writing plus ... which for some reason you really like, I make this symbol and you're like, no, it's the same concept, ... forever, ... forever, go up to here. I keep with your ellipsis, none of your sigma crap. When n equals 0, I put n equals 0 in this formula here in the first term. So that will give me t, let's just do the first term. That's going to give me 0 factorial, 2 times 0 factorial, over 2 to the 0, 0 factorial squared. It's on a slight slant too. Happy Gilmore, he's only got one shoe on. He's like, where were you on that? Where were you on that one? Slightly slanted, because I got one shoe on. Actually, I actually have a dip right here. This is times pi over 2 times k. It goes to 0. Sine of 0 is also 1. So what do I get? I just get pi over 2. What's the second term? You're like, I already lost it in the first. I don't want to see it. Too bad. And then what am I going to get? 2n factorial, which is 2 factorial. 2 is what? So that gives me the pi over 2 again. And then we're just going to get sine squared theta naught over 2. That wasn't so bad. What does this say? T is equal to 4 root L over G times this power series, which for the first two terms is equal to pi over 2 plus pi over 2 sine theta naught squared plus ... plus hot. Higher order terms. Don't get excited. Well, get excited, but not for those reasons. For the mathy reasons, hot. Pi over 2 could come out of that. And just write it as a 1er times sine plus hot. Pi came out of all the hots. Hot pi, hot pi. Let it cool down, then eat it. What does that give me? 4 over 2 is 2, and we get collapsing this if you want to get rid of all the higher order terms, including that first approximation. The first approximation, the first term of this power series is a 1er times Huygens constant, which is going to give us what? The period is approximately equal to pi over 2 times 4 times root L over G, which is equal to 2 pi root L over G, or Huygens law. Please subscribe right here. You can follow us at Facebook. Do this social media crap. I hate saying these things. Okay, let's try it again. Subscribe right here. Follow us on Facebook at Adrian the Tutor. Follow us on Twitter at Tutor_Inc. I'll see you next time. We're going to do a bunch of series about don't just do math problems if you don't like them, especially if someone's trying to make you do homework or do some derivative or do something like that. Try to find a problem in the back of the book where you actually do something like the pendulum and all the horrible moves that I had to do, and you watched right to the end. Haha, gotcha. All of those horrible math moves were done for one thing. I really wanted to know what the period of a simple pendulum was more than Huygens did. See you next time. T is equal to 4, the square root of L over 2. How did that, the whole time you sat there and let that be a 2. G units. G unit. It's a G, gravity. What the hell, cameraman? I'm just kidding. I have to blame someone. It wasn't me. Who else is there?